Howdy. And so we've seen the periodic trends that as we move up and to the right, the strength of electrostatic attraction between the outer electrons and nucleus increases, the size of the atoms decreases, the ionization energy increases, electron affinity increases, and the electronegativity increases. And this is consistent with how we describe metal elements and non-metal elements. And so the metal elements are the ones in the red, the non-metal elements are the ones in the blue. The metal elements tend to react by losing electrons. They have lower ionization energy. The blue elements, the non-metal elements, tend to react by gaining electrons. They have more positive electron affinities. And so when a metal element and a non-metal element react, they form an ionic compound. Electrons are transferred from the metal to the non-metal. Now, if two non-metal elements react, they form a covalent bond. They form a molecular species. And so this video is on covalent bonds. And covalent bonds are important because all molecules are held together by covalent bonds. By understanding covalent bonds, we can understand why molecules form. Now, after watching this video, you should be able to describe how when non-metal elements react with each other, covalent bonds are formed. Describe how the more electrons being shared, the stronger the covalent bond and the shorter the bond. And also the shorter the bond, the stronger the bond. Given a series of bonds, you should be able to put them in order of increasing strength. Given a Lewis diagram, you should be able to determine the bond order of each bond. Given a formula, you should be able to determine the name of the molecule. We'll see that naming molecules is different than naming ionic compounds. For ionic compounds, you never ever use di, tri, or tetra. When you name molecules, you actually use the di, tri, or tetra. And so a question you could see is, what is the chemical formula of the compound formed from magnesium and oxygen? Now, magnesium is a metal. It's alkaline earth metal, and oxygen is a nonmetal. And so the magnesium is going to lose electrons to the oxygen, and they're going to form an ionic compound. Now, because magnesium is going to form a +2 ion, and oxygen is going to form a -2 ion, the ratio is going to be 1 to 1. And so you get magnesium oxide. Now you should remember that the formula for ionic compounds is an empirical formula. It just gives you the ratio of the ions. And so if we start with the elements in their standard state, magnesium is a metal and oxygen is a gas, O2, and then they form the MgO. And so because we have two oxygens in the O2, we need two magnesium, so we add a 2 in front, and then we form two MgO formula units.
To demonstrate the formation of an ionic and a covalent bond and their differing properties, we have a piece of magnesium ribbon. Magnesium ribbon can be burned in a flame. I'm going to lower it then into this can to protect our eyes so that we don't look directly at the bright white light. The white product formed is the white magnesium oxide. An ionic compound is formed when magnesium reacts with oxygen. It's a very stable compound, as is evidenced by the large amount of heat and light that's released.
And so we went from a metal, magnesium, which is springy, lustrous, and a gas, oxygen, and we formed a ceramic magnesium oxide, an ionic compound. And so again, there was a transfer of electrons from the magnesium to the oxygen. Now, another question you can see is, what is the chemical formula of the compound formed from sulfur and oxygen? Now here, sulfur and oxygen are both nonmetals. And so because they're both nonmetals, they should form a molecular species. They'll form covalent bonds that are going to share electrons. You can also think in terms of electronegativities. They're fairly close on periodic tables. On the periodic table, they have similar electronegativities, and so they're going to share electrons. Now, sulfur and oxygen can actually form a couple different species. Probably the most common is SO2. You can also form SO3. And so again, in elements in their standard state, you have sulfur solid plus O2 gas, and then you get SO2.
Here we have a piece of roll sulfur. We can take a small piece of the roll sulfur and place it in the deflagrating spoon. We're going to heat it in the spoon, and the sulfur will melt and ignite. Then we're going to lower it, once it has ignited, into this bottle of oxygen gas so that the flame will be more visible. Sulfur burns with that lavender flame, producing sulfur dioxide gas, SO2. Sulfur dioxide gas is a covalently bonded compound.
And so when two nonmetals react, they tend to form covalent bonds and molecular species. And so we can consider H2. And so imagine that we have two hydrogen atoms infinitely far apart, and then they come close together. Now, as they get closer, what's going to happen is each nucleus is going to be attracted to each electron, both electrons. And so you're going to increase the electrostatic attraction between the electron and the nucleus. The stronger the attraction, the more stable. The stronger the repulsion, the less stable. And so as the two atoms come closer, you'll have some electron-electron repulsion, you'll have some nucleus-nucleus repulsion, but you'll also have the electron-nucleus attraction, and it's the attraction that causes the formation of the bond. And so again, imagine infinitely far apart. We assign that energy to 0. As they come closer, you're increasing electronucleus attraction until you get to that minimum, and the minimum is the most stable configuration. And then if you keep on getting too close, then you'll start getting nuclear-nuclear repulsion, and it's going to start getting less stable.
When the H atoms are far away from each other, we designate the energy as 0. As they move closer together, they attract each other more and more, and the energy decreases to a minimum. At this point, a stable hydrogen molecule is formed. If the nuclei come any closer, the energy increases rapidly as nuclear and electron repulsions take over.
And so remember, the stronger the attraction, the lower the energy, the more stable. The stronger the repulsion, the higher the energy, the less stable. Now, the difference in energy between that minimum and when the hydrogen atoms are instantly apart is the bond energy or the dissociation energy. It's the amount of energy required to break that bond. The larger the dissociation energy, the lower the energy of the bond. The stronger the bond, the higher the bond energy, hence the more stable. Now, it's also important to remember that atoms are always vibrating. And so even though you're at that minimum, it would seem that to be, once the two atoms get to that minimum, they're static, but atoms are always vibrating at the atomic level. And the bond length is equal to that minimum, but that minimum is the average distance between the two nuclei.
Let's zoom in closer to see the overlapping atoms in more detail. When the atoms are far apart, they do not feel each other. But as they come closer, the nucleus of one atom attracts the electron cloud of the other, and the attraction draws the atoms still closer. Note the increasing electron density between them. Soon, the electron clouds interpenetrate. Attractions dominate, but repulsions between nuclei and between electrons become stronger. At the point of lowest energy, attractions just balance repulsions, and the two H atoms exist as an H2 molecule. The covalent bond is the mutual attraction between the nuclei and the electron pair. If the nuclei were to move closer, repulsions would outweigh attractions. The increase in potential energy would destabilize the system, and the atoms would move apart again. In reality, the molecule vibrates, the atoms moving slightly farther and closer at the point of minimum energy. The bond length is the average distance. For H2, it is 74 picometers. The bond energy, the difference between the minimum energy and the starting point, is the energy needed to break a mole of H2 molecules into separate H atoms. For H2, it is 432 kilojoules.
And so it's kind of cool. What we can see is actually the smaller the atoms, the closer the atoms, the stronger the bond. Because if the atoms get closer, you can increase the electrostatic attraction. And so we can compare H2 versus Cl2, Br2, and I2. And H2, smaller, closer, stronger bond. Cl2 is going to be smaller and closer than Br2 and the I2. Remember, it just follows the periodic trends. As you go down the periodic table, the atoms actually get bigger. And so iodine is going to be bigger than bromine, which is bigger than chlorine, which is bigger than hydrogen. And so the smaller the atoms, the closer the atoms, the stronger electrostatic attraction, the stronger the bond.
Now let's compare H2 with Cl2 and other halogen molecules. The much larger chlorine atoms reach the energy minimum and form a Cl2 molecule at a greater internuclear distance. Because the Cl nuclei are farther apart, it takes less energy to separate the atoms, thus a greater bond length and a smaller bond energy. Moving down group 7A, bromine is larger still, so we would expect an even greater bond length and smaller bond energy. And iodine, the largest of these halogens, continues the trend to longer, weaker bonds. Stepping back, we see that in each case, mutual attractions draw the atoms together and they form a covalent bond of specific length and energy.
And so in general, the smaller the atom, the closer the atom, the stronger the bond. And so we can see H2 has a dissociation energy 436 kilojoules per mole, a bond length of 0.74, while Cl2 243 and 1.99. Now this is a good generality, but it's not always true. There are other considerations. And so if we consider H2 versus HF, H2 hydrogen atoms are smaller, and so you actually do get a smaller bond length of 0.74. HF, you have 0.92, but notice that the HF is a longer bond, but it also has a larger dissociation energy. And so that could just be because of the more positive nuclear charge of the fluorine. But in general, the smaller the atom, the closer the atom, the stronger the bond. And so we can use the size of the atoms to actually kind of determine what is the relative strength of a bond and the length of the bond. But actually the number of electrons being shared is a better indicator of the strength of the bond. And so atoms can share different numbers of electrons from 1 up into 8. The more electrons shared, the stronger the bond. Now the number of electrons being shared is characterized by what's referred to as the bond order. Now the bond order is just the number of pairs of electrons being shared between two nuclei. And so when we write a single line, that means a pair of electrons. And so for a single bond, you have 2 electrons being shared, and that would be a bond order of 2. Now if we draw 2 lines between 2 atoms, each line corresponds to 2 electrons, so 2 lines would be 4 electrons being shared, and that's 2 pairs, and it gives you a bond order of 2, and so that's a double bond. Now a triple bond we draw with 3 lines, and so that would be 6 electrons being shared, and that would be a bond order of 3. Again, bond order is a number of pairs of electrons being shared. And so if you got a single, double, or triple bond, it's really pretty easy. That corresponds to bond orders 1, 2, and 3. Now sometimes things will be a little bit more difficult, and so we want to use an equation to determine bond order. And so bond order is equal to 1/2 times the number of electrons being shared divided by the bonding regions. Now again, if you have single, double, or triple bond, it's easy, bond order 1, 2, and 3. This is just to show you that the equation works. And so we have 1/2 for the single bond, 1/2 times 2 electrons being shared divided by 1 bond region, that gives us 1. For the double bond, 1/2 times 4 electrons being shared, 1 bond region, 2. And for the triple bond, 1/2 times 6 over 1 gives us 3. But when I mentioned sometimes things are a little bit more complicated, here we can look at ozone. And so notice that we have 3 oxygens, and the 2 bonds between the oxygen should be equivalent. There's no reason that they are different. And you notice that you have a single line and then you have a dashed line. Now, that corresponds to actually each 2 atoms are sharing 3 electrons, or there's a total of 6 electrons being shared divided by 2 bond regions. And so to use our equation, we have 1/2. Again, we have 6 electrons over those 2 regions. So 6 divided by 2, and that gives us a bond order of 1.5. And so bond orders do not necessarily have to be integers. Now, we can do this with these 2 bonds because those 2 bonds should be exactly equivalent. Okay, and we'll see later that those 2 structures for ozone are what referred to as resonance structures. And so bond orders are typically specific for specific bonds, except that the bonds are equivalent. And you should be able to determine bond orders from the Lewis diagrams. And so here we see when we have a single line, that's a bond order of 1, 1 pair of electrons being shared. When we have 2 lines, again, each line represents 2 electrons. That's a double bond, bond order of 2 pairs of electrons being shared. And when we have 3 lines, that corresponds to 2 electrons per line. That gives you 6 electrons. And so that's a bond order 3. Again, bond order is number of electrons being shared. If we look at something more complex, and so notice on this ring structure, and so you got the 1, 2, 3, 4, 5, 6 bonds. Now you got 18 electrons being shared, and so 1/2 times 18 over 6, and so that gives you a bond order of 1.5. And so again, bond orders do not necessarily have to be integers. But those carbon-carbon bonds in the ring should be equivalent, and that's why we can use the equation that we did. And so if we look at the carbon-carbon single bond versus carbon-carbon double versus carbon-carbon triple, obviously the bond orders are 1, 2, and 3 correspondingly. Now it's kind of interesting. Look at the lengths, in picometers. Pico is 10 to the minus 12. And so notice that the more electrons being shared, the shorter the bond. That may seem a little bit counterintuitive. You have more electrons being shared, and the nuclei can actually get closer because the nuclei are actually shielded better, and so they can get closer. And so more electrons shared leads a shorter bond. Also notice on the energy, the more electrons shared, the higher the energy. Now, you should notice that a single bond a triple bond is not 3 times as strong as a single bond. And so the triple bond is 837 kilojoules per mole. Now, if you had 3 single bonds, that's 1,044. And so a triple bond does not have the energy 3 times a single bond. It's going to be a little bit less, and later we'll see why that is. A double bond is not twice as strong as a single bond. And again, it's because the double bond is a little bit different than 2 single bonds. But more electrons shared, the shorter the bond, the stronger the bond. And again, a double bond is not quite as strong as 2 single bonds. A triple bond is not equivalent to 3 single bonds. But the stronger the bond, the larger the bond energy, the shorter the bond distance. More electrons shared, the stronger the bond, and the shorter the bond. And again, the bond order is the best indicator of bond strength. And so here we had carbon-carbon-carbon. We can also look at carbon-oxygen. And so the carbon-oxygen single bond, carbon-oxygen double bond, carbon-oxygen triple bond. And so again, we see the same trends. As we share more electrons, the bond length gets smaller, the bond energy gets bigger. And so the more electrons being shared, the larger the bond order. Again, bond order is just the number of pairs of electrons being shared. More electrons being shared, the stronger electrostatic attraction between the electrons and nuclei. The smaller the atoms, the closer the atoms, the stronger the attraction. The stronger attraction between the electrons and nuclei, the larger the bond energy. The lower the potential energy of the bond, the more stable the bond. And again, the number of electrons being shared is the most important factor. And so finally, we're going to talk about nomenclature of covalent bonds. And so when we talked about ionic compounds, we saw that we never ever use di, tri, or tetra. For ionic compounds, you're expected to know how many of each you have based on the charges of the ions. For covalent bonds, often we have to use the di, tri, tetra to indicate the number of elements. Now, to give you some examples, here we have nitrogen monoxide, nitrogen dioxide, dinitrogen trioxide, dinitrogen pentoxide. And so nitrogen and oxygen can actually form, there's actually more than 4 distinct compounds, but they can form at least 4. There's more than 4, sorry. And we have to be able to name these different ones. And so for molecular species, we have to use the mono and di to indicate the relative numbers. Now it says use prefixes on how many atoms there are in each type, except for someone that never has mono. And so we have nitrogen monoxide, nitrogen dioxide, dinitrogen trioxide, and dinitrogen pentoxide. But again, we do not use mono for the first element. And so we look at some examples. And so for water, we'd call it dihydrogen monoxide, sulfur hexafluoride, sulfur trioxide. Now, SO3 2-, that's a sulfide ion. And so that's one of the polyatomic ions you should recognize. Nitrogen trihydride, which is ammonia. Now again, calcium chloride is an ionic compound, And so for ionic compounds, we never use the di-trior-tetra. And then magnesium nitrate is also ionic compound, so we do not use the di-trior-tetra. And so please remember, when a metal element and non-metal element react, you form an ionic compound. When two non-metal elements react, you form a covalent compound or molecular species. Remember, the more electrons being shared, the stronger the bond and the shorter the bond. I hope that was helpful.